Welcome, everyone. My name is Jim Olsta, and I am the session chair of this group of presentations. This session is titled Environmental. A couple of things to note before we start these presentations. You will have the opportunity to ask questions during this on-demand session by clicking the Questions button at the bottom of the video window. Your question will be sent to the presenter to answer as soon as they are able. To claim PDH credits for this session and any other education session, you simply need to click on the Claim Credit button on the conference homepage. From there, you will fill out the survey for any sessions that you attend. Please note that you will need to include the verification code shown in this session to verify that you did attend this session and ensure that you receive the proper credits. Please enjoy the presentations. Thank you.
Hello, yes, my name is Neil Nowak and I work for SCS Engineers as a project director. My topic is HDPE line produced water evaporation and recycling ponds. The water is collected and stored and evaporated in these commercial fluid ponds that are topped with high density polyethylene as top layer. So water is generated from the production of oil and gas, where several billion barrels of production water and flowback water are generated each year. The water is collected and is either put in the pond for evaporation or storage and recycling. So here's an illustration of the way that the product of the oil and the gas is removed from the ground and brought to the surface. The old way of drilling is a conventional drilling where it's basically a vertical penetration into the formation and the material is sucked out like a straw. And the new way of drilling, or the unconventional drilling, which is actually now the most prevalent drilling method, is hydraulic fracturing or horizontal fracturing through these different layers down in the production zones of the shale. As you can see, the two different illustrations are, one is a jelly donut and one is a tiramisu cake, which is a pretty good way of illustrating the different ways that the product is withdrawn. Here's an illustration of the United States and the different states where oil and gas is produced, and as you can see, that Texas is the largest of the states of where produced water is generated. Oklahoma, Texas, California, and Wyoming are the four largest states where produced water is produced. And in Texas, the Permian Basin, which is in West Texas, and also it extends into the southeast area of New Mexico, is the most largest oil and gas producing region in the United States. Here's another slide that depicts the amount of produced water generated per barrel of oil equivalent. So in the Permian is where the oil or the gas is withdrawn, and for oil, water, there's 4 times the amount of water times 1 barrel of oil. That's a lot of water. In 2018, the Railroad Commission of Texas estimates that 10.7 billion barrels of water were produced in the Permian. 46% of that was recycled and 54% of that was injected. Only 2% of the state's fresh water is used, and then regulations will definitely drive water towards recycling and away from saltwater disposal wells. So most recently here in 2020, the different areas as well, showing you the different percentages of the amount of water that is actually recycled in these different areas. And the Permian Basin is now up to about 64%. The Delaware Basin in New Mexico is 90% recycles. And as you can see, the other areas are striving to have higher recycling percentages. Here's the graph showing the trends of produced water in Texas over the last couple of number of years. And as you can see, starting in 2016 all the way through 2018, the amount of oil and gas is increasing with regards to also the amount of produced water. 2020 was probably not shown here, but it's probably a flat line or probably reduced because of the coronavirus issues and the downturn in the oil and gas industry. So the technologies managing produced water include injection, recycle, reuse, frac injection, treatment for surface discharge, and evaporation. In Texas, the Railroad Commission Rule 8 regulates the recycling and reuse of the water in that state. Part of the regulations call for pits lined with hydraulic conductivity of 1 × 10⁻⁷ or less, 2 feet of freeboard, and they like to see the ponds be double lined with a leak detection in between. As far as recycling goes, the stationary fluid recycling is a commercial facility that's fixed and will have fluids coming to the site and then reused for hydraulic fracturing. In order to get the permit for these type of facilities, it's pretty stringent, where you have to have an engineering geologic information, siting, design requirements, operating monitoring, closure cost estimate, and it's a pretty extensive amount of material that goes into a permit application. An H11 pit form is basically the form that is used as a application cover, and then everything behind that is all the technical information. And here's a typical liner design with a 60 mil primary, a leak detection of a 200 mil geonet in between, and a 40 mil HDPE secondary. And they've also gone to a geosynthetic clay liner below the secondary as a tertiary or additional liner. Here's an aerial photograph of a dual pond system here, 2 500,000 barrel ponds that are about 20 feet deep. Both of them will be double lined with leak detection, where the total amount of water stored in this facility will be about 1 million barrels. Here's the same facility with both ponds completed. There's some rainwater sitting in there and some algae growth before the operations are starting. But you can see that it's a pretty robust system, and the white liners that you see there are rub sheets for pipes that go in and out of the pond for reusing and recycling the water. Here's a single pond similar to the other two, with the berms built up around, and that's soon to be lined with HDPE. Okay, why use HDPE or high density polyethylene? Well, the ultraviolet degradation resistance, and you can see that the durability of this material as exposed without being buried is very good. Very good chemical resistance. The black color can actually enhance the evaporation of water. HDPE was chosen over different other materials compatible with site conditions, and also use the texture to help with the slope stability. And as you can see, the strength characteristics of HDPE over time, very good compared with other geomembrane liners, as you can see here from some testing that was done back in 2016. So the liner is deployed and installed on the side slopes and then welded together and placed in the anchor trench. Here you can see the adjacent panels being welded together. I've seen this before. This is just the welding of the liner. And through proper CQA techniques and testing, strength testing during construction, here is a field tensiometer doing field tests for pre-welds and making sure that the liner is installed up to the specifications. Here is a pond being constructed, and you can see the three different layers, the secondary, and then you can see the net in between, and then the primary on top. These are the three layers as it's being constructed. Here's a photo of the construction of a pond that has a liner leak detection system with lay flat pipe in order to assist with the leak collection down to the low point or the sump for the leak riser. Here's a photograph of the Danish Flats project with 14 ponds at about 5 acres each. And you can see that that's a lot of water out there being collected, and this is an evaporation system. This is a total of about 6.5 million barrels of capacity out there in East Utah. Here's another facility. This is in southeastern Wyoming, where ponds were being constructed similarly, double-lined with leak detection in between. Each one of these ponds is about 600,000 barrels of capacity. Here's the facility under construction and shows you the different layers. In the distance there, you'll see the gray, that's the GCL layer. And then to the left of that is the secondary layer being placed. And along the slope is also some of the GeoNet being deployed over the top of the secondary. So produced water is delivered to these sites, several sites by truck and offloaded through an offloading facility that takes the water and separates the oil from the water, because when you drill, you'll have about 1% of the water that comes to it as a disposal with oil in it, and you want to get rid of that before you put that out into the evaporation ponds. Here are trucks being offloaded through the gun barrel system. So the trucks have a little pump on the back there, and they push the water out. That water then is pushed out through the gun barrel system, where the oil and water are separated. And then from this, the oil goes to the oil recovery tank, and the water goes to the last stage of separation, or the skim pond. It's good to note here that the water is sometimes delivered by pipeline to the facilities, and typically that the pipeline facilities are the recycling facilities where the water can be delivered and then also withdrawn using the pipeline system for delivery back out to the field for use. Here is a photograph of the last stage of separation, or the skim pond. So it goes from the gun barrels through the skim pond, and then from here out to the evaporation ponds. And here's a shot of a typical evaporation pond after the water is delivered from the skim pond. So evaporation, when you take these ponds and you put the water out there, the water tends to evaporate, and the climate at these sites is semi-arid and ideal for this. Also, the black liner aids in the evaporation. The water is about 10,000 to 70,000 parts per million total dissolved solids, typically about 30,000. When you talk about evaporation, you're talking about the water cycle. Here's just a USGS illustration of how that works. And the water is picked up out of the ponds and then brought up into the atmosphere, and then it goes up to so it's almost a recycling of the water back into nature. So evaporation in Wyoming, for example, here's your free water evaporation annually, and typical is about 45 inches per year. In West Texas, where the Permian is, out in the Big Bend country and the Panhandle Plains, the evaporation can be as high as 68 inches of net evaporation. Evaporation is ideal when the air temperature is above 80 degrees Fahrenheit. It's sunny, low humidity, the wind is blowing, and then the water in the ponds is really best if it's not deeper than like 3 feet deep. so the sun can penetrate through the water and heat up through the liner. So the different facilities where the evaporation was estimated, 50 and 40 and 45 inches, when the liner was placed in there and then actual evaporation was measured, the increases were about 17 to 30% higher because of the liner over time. One way of enhancing the evaporation was using these drip legs that were used to put the water out onto the liner, the hot liner that had a southern facing exposure. And this liner here is in eastern Utah, where the temperatures would typically get above 100 degrees, and that water would come out onto the hot liner and would be enhanced, evaporated through that system. Also, another way of enhancing evaporation was to use atomizers that spray a fine mist above the water, and you could get about 5,000 barrels of evaporation a day, depending on how many of these evaporators you use and for how long and what the temperature is for that day. So maintenance after several years of operation, possibly 8 to 10, depending on how much dissolved solids are in this water, the brine or its salts build up in the pond, and if it does excessively build up, then the sludge or the sediments need to be removed, and either removed or facility buried with them. It depends on the state, but some regulations they allow that material to be buried if the material doesn't have a high amount of oil in it. Here's a pond showing you there was a repair that needed to be done, so the water needed to be removed. And this was after about 7 years of operation, and you can see that the sediments are in the bottom here. Probably a lot of this happens to do with wind-blown sand or dirt. Being in Wyoming, there was a lot of wind that probably blew this into the pond, but this is the amount after about 7 years of operation, and these ponds were about 15 feet deep. So we've had to find a leak. We found a leak, and then it had to be repaired. So the liner had to be exposed where the leak was found. So getting down to where the leak was, the liner had to be exposed using plastic shovels and also power washing and all by hand, wheelbarrows to be removed or move the sediment out of the way, and the liner cleaned and repaired. Please note that a lot of these ponds are constructed not with black liner but with white liner. So the white liner tends to be lower temperature, right? So that reduces the ability of the liner to heat up the water, and therefore reduces the evaporation, and also reduces wrinkles due to less deformation of the heat and cold effects on a black liner. Ponds can also be covered. Here's a pond that is covered with HDPE or white HDPE, and then the vapors are collected and off-gassed here, and then through and then destroyed. It depends on what the product is that you're holding here, but sometimes you need to do that to lower emissions if the regulations in the area call for that. A lot of times now the liners are put in with a conductive liner, and so therefore can be found with a wand, and even pinholes can be found just after installation, and therefore when you install these ponds, the leak amount is minimized. Here's another photograph of produced water ponds for recycling out in the Permian Basin of Texas. Conclusions are that the HDPE is a very good product to use for lining the ponds. Very good high durability and UV resistance, and you can also have it as black or white to help with either evaporation or reduce evaporation and reduce the wrinkling. And here's a slide. I just get a kick out of this slide. An electric vehicle station being run on diesel. It doesn't seem to make sense, but there it is anyway. Thank you very much. My name is Neil Nowak, and you can see my contact information right here. And please contact me if you'd like to know more about these type of.
I am Abigail Gilson from TRI Environmental, and my paper, entitled Dipole Measurement Density and Dipole Spacing, covers a very important aspect of performing electrical leak location testing on covered geomembranes. Electrical leak location methods are the most technologically advanced way to detect leaks in installed geomembranes, and testing covered geomembranes is the only way to detect the most significant damage caused to installed geomembranes. This would be the kind of damage that's caused during cover material placement directly from the equipment or the dozer, also due to punctures occurring before or after cover material placement. There's two ASTM standards for covered geomembrane testing, but neither of them includes any information about the testing relevance of the dipole spacing. ASTM D7007 uses an increase in measurement density to improve the, quote, sensitivity of the testing method, but it's never been quantified before. The problem with changing measurement density as a function of sensitivity is that sensitivity is a function of site conditions. So a company performing leak location will assume a measurement density when they bid on a project, and then when they get to site, they sometimes have to increase that measurement density. Therefore, the cost of the testing is going to go up unexpectedly, and it's also going to negatively impact the construction schedule. This research presents the first rough field quantification of an increase in dipole method sensitivity as a function of measurement density and dipole spacing. For those of you not familiar with the dipole method, the name comes from the instrument used to acquire data. This photo here is of a simple 1 meter dipole instrument. It has 2 feet, we call them the front foot and the back foot. These are reference electrodes filled with copper sulfate liquid so that it doesn't react with the cover material. We need to pick this instrument up and advance it along a survey line, sometimes called a transect. And every time we set it on the cover material, we take a data point, a measurement. So these string lines are set throughout the survey area at some specified spacing. To perform the dipole method, a DC voltage is applied to the cover material via a current injector electrode, and the return electrode is connected to the underlying conductive layer. Voltage drops occur at locations where the electrical field is connected to ground, which would be where there's a leak or a breach in the geomembrane. So this dipole can be used to pinpoint where those voltage drops occur, so the leaks can then be excavated for repair. The voltage measurements are taken in a grid pattern throughout the survey area, which is referred to as the measurement density, but measurement density would be more like 1 data point per meter square, which is not really appropriate or descriptive enough for the dipole method. So you're mostly going to hear me say grid spacing. So an example of grid spacing would be 3 meters by 3 meters or 1 meter by 1 meter. So for example, 1 meter by 1 meter would be you're taking data points every meter along a line, and each line is spaced 1 meter apart. The measurement density should be determined by the leak detection distance. The leak detection distance is how far away the dipole can be from a leak and still pick it up. The dipole spacing, or the distance between the measurement points on the dipole apparatus, is not specified by any ASTM-based testing methodology. But after a literature review, the one location that states the relative importance of dipole spacing to leak detection sensitivity is in a paper by Lugli and Mahler. They state that the leak detection distance is proportional to the dipole width. So this paper is a field examination of the dipole spacing. Both a plan view and a cross-section of what the voltage field does over a leak is shown here. So this bullseye pattern has very tight contours in the isopotential voltage lines right or over a leak. And the surface will sharply decrease over a leak and then sharply increase the gradient of the potential surface. The dipole will measure from front foot to back foot. As it travels across the leak, it'll measure a negative gradient. And then when it's on the other side of the leak, it will measure a positive gradient. What this looks like in terms of voltage values is shown by the red line below. So as the dipole travels and approaches the leak, you get a sharp decrease in the voltage. It passes through zero, and then you have a peak in the voltage field, and then it tapers back down. If the dipole is not directly over the leak, but it's going past the leak at some transect at a given offset, you'll still see the leak signal shape, but the curve will be softer and the peaks will be of smaller magnitude. This is a voltage map created using the dipole method. What we do is we color code the map to represent negative and positive values. So in this case, green going to yellow going to white is positive voltage values in increasing magnitude. Red going to blue going to black is increasingly negative voltage values. In the middle of the map, you see the current injector electrode. So you have the bottom of the current injector is positive and the top is negative. This is because the dipole was facing vertical when it acquired data from bottom to top. So when it's walking toward the current injector, it has positive gradient. When it's walking away from the current injector, it has a negative gradient. So what we're looking for is a pattern that represents the opposite of the current injector. It's where the voltage is going out of the pad rather than in the pad. So leak locations end up looking like sort of like butterflies on their side. They have a negative bubble directly below a positive bubble, and these little bubbles are separated by very closely spaced contour lines. So we can see an example of a large leak signature on the bottom right and a small to medium-sized leak signature as leak number 2. Both the measurement density and the dipole spacing affect the leak detection sensitivity. For measurement density, the closer the dipole is to the signal, the stronger the signal is going to be. So if you have a higher measurement density, you will get a larger signal. It's never been correlated with dipole spacing in any of the ASTM-based standards. For dipole spacing, a larger dipole crosses more voltage contours, so you're going to get a larger voltage reading with a larger dipole, i.e. a larger signal. Dipoles larger than 3 meters or 10 feet are physically difficult to manage, so 3-meter dipoles are typically the largest used. But dipoles measuring 1 meter or 3 feet are also much more common than 3-meter dipoles. My approach to quantify just how much measurement density and dipole spacing affect the sensitivity was, for one, create an electrical signal that signifies a leak and use different measurement densities with the same dipole to measure that signal. Then use the same measurement density with different dipole sizes to measure that signal. And the way I'm doing that is by creating an offset from the signal that corresponds to a given measurement density. The way I'm going to be reporting the signal strength is through the 2 different methodologies. So D7007 is actually better to quantify signal strength, and D8265 is actually better for quantifying leak detection distance. Let me explain why that is so. D7007 uses a graphical data analysis where you plot the values of voltage on the y-axis with the x-axis being your survey transect. So you can observe the sine wave pattern of the signal, and you can measure peak to peak, negative peak and positive peak, the amplitude of that signal. ASTM D8265 requires voltage mapping, like the map that I showed you previously. So the leak detection distance is visible in the plan view. What makes a leak detectable is that when the dipole is facing the current injector, it should be observing a positive voltage gradient or a positive voltage value. But when there's a leak between you and the current injector, it observes the negative gradient or the negative values. So when you're looking at a plan view, the detection sphere is anywhere that you see red on the map. That's where you start to be able to detect that leak. So viewing it in plan view shows you the true detection distance. So for this data that I analyzed, I'm walking along a transect. So you can just visualize a transect as occurring next to this leak signal in plan view. So what you're going to be viewing is a vertical map of a slice of that data. So in the beginning, you should see negative values, and that shows you how far away you can be to detect that leak. And then you have positive values once you pass the leak. To do these comparison trials, an electrode was inserted into a soil layer to provide a simulated leak signal. A physical grid system was set up on one side of the simulated leak using physical static measuring tapes to represent a 3 meter by 3 meter grid spacing, because 3.05 by 3.5 is the maximum prescribed by D707, a 1.5 meter by 1.5 meter grid spacing, and then a 1 meter by 1 meter grid spacing, which is the minimum prescribed by D707. It's important to note that the grid system was created for each dipole size, so that each dipole would straddle the simulated leak so that there was never an advantage given to one of the dipole sizes. 2 different dipoles were used using the same reference electrodes for the feet, a 3 meter spacing and a 1 meter spacing. Multiple readings were taken for each run, then averaged to reduce the noise. The first 4 trials were used to directly compare dipole spacing and measurement density. So I used 2 different dipoles at 2 different grid spacings. And then the 5th trial was used to compare runs where the dipole spacing was equal to the grid spacing. Here are the results of trials 1 and 2 plotted at the same y-axis scale. The leak detection distance was calculated by measuring the distance between the simulated leak and where the negative voltage values start on the vertical bars. Signal strength is calculated by the peak-to-peak voltage values. Here are the results of trials 3 and 4, also plotted at the same y-axis scale. Each of these pairs shows the difference in signal strength between the 3 meter and 1 meter dipoles at the same measurement density. Here's trial 5 on the left, plotted at the same y-axis scale as trial 2, to show the difference in signal when using a dipole with a spacing equal to the measurement grid spacing. What's interesting about this comparison is that the signal strengths are about the same when you're just looking at the y-axis values, but the leak detection distance of the 3 meter dipole is still larger, since the sine wave pattern has a larger peak-to-peak distance along the x-axis, or survey transect. And when you look on the left side of the graph here, the 3 meter dipole provides a stronger negative value further away from the simulated leak. A summary of all of the signal magnitudes and estimated leak detection distances is listed on the table below here. Let's make sense of the values in the table by comparing them. So first, we're just going to look at signal strength. When you compare the different dipole spacings, the signal strength increased by 315% when you use a 3 meter versus a 1 meter dipole at a 3 by 3 grid spacing. At the smaller grid spacing, the 3 meter dipole increased signal strength by 176% when compared to a 1 meter dipole. If you want to compare the increase of signal strength based on measurement density, the 3 meter dipole increased signal strength by 190% when quadrupling the measurement density, and then the 1 meter dipole increased signal strength by 337% when quadrupling measurement density. But if you're looking at leak detection distance, the 3 meter dipole exceeded the limits of the testing area in all cases, but the 1 meter dipole only exceeded the testing area when it was at a 1 meter by 1 meter measurement density. So let's look at the 1 meter dipole trials to quantify the increase in sensitivity based on measurement density increased. And that was actually only 11% when quadrupling the measurement density. Let's take a closer look at how an increase in measurement density improves, quote, sensitivity. So there are two curves here. One is the 3-meter dipole to 3x3 spacing, and one is a 3-meter dipole to 1.5 by 1.5 meter grid spacing. When you look at these sine wave patterns, the leak detection distance is basically the same. What happens is as the dipole gets closer to the leak, it gets a larger signal magnitude. So it gets these two little bumps in signal strength as it gets closer to the leak. But the truth is that the leak detection distance doesn't change. There are a few conclusions we can draw from looking at this data. The first one, and most importantly, dipole spacing determines leak detection distance. So this confirms the analytical findings of Lugli and Mahler. So this makes dipole spacing a much larger factor in sensitivity than measurement density. Also, it shows that the indirect method of finding the leak detection distance based on the signal strength, the way it's done in ASTM D707, is fundamentally flawed. We've also found out that there's little to gain when increasing measurement density from a grid spacing that's equal to the dipole spacing. Although signal strength is slightly greater at a greater measurement density, it does not change the leak detection distance for a given dipole spacing. And lastly, even at a spacing of 1 meter by 1 meter, a 1 meter dipole is not quite as effective as a 3 meter dipole at a 3 meter by 3 meter spacing. So this shows us that a survey that requires 9 times more data points is in fact not as sensitive as a survey performed with a 3 meter dipole. Let's discuss the practical implications of these findings. Even though a larger dipole results in a more sensitive survey, it's probably not appropriate in an ASTM standard to specify exact dipole spacing. However, project-specific specifications are the appropriate place to specify a dipole width in order to maximize the survey sensitivity. As far as the ASTM standards go, they could definitely be improved by simply requiring that the measurement density is determined by the dipole spacing. So a 1 meter dipole uses a 1 by 1 grid, 3 meter dipoles use 3 by 3 meter grid. If measurement density is standardized, then the bidding process is much easier. So a contractor knows ahead of time the measurement density that they're going to use so that it can provide a precise cost for the survey. And also, construction schedule won't be impacted. So they won't end up doing a higher measurement density than they proposed during the bidding process. I really appreciate your interest in this research, and I'm certainly happy to answer any and all questions regarding this or anything related to electrical leak location at this contact information provided here. I look forward to hearing from you.
Hello, my name is Greg Pignataro along with Evan Bao, and we will be presenting a case for technology implementation to evolve geosynthetics. This presentation explores feasibility in applying automation technology to further mature geosynthetics. First, a brief analysis of proven implementation principles by other industries, followed by an objective look at points of entry for automation tech within the current geosynthetic supply chain. Then, target specific applications with the best return on value, and finally, conclude with examples of cyclical benefits for the industry with an improved automated process. Automated technologies are proven to provide a great deal of potential to re-engineer and improve core business practices. In many cases, those improved processes will operate in a more resourceful way, freeing up time previously taken by humans to perform redundant, repetitive activities. A brief examination of some well-known businesses and industries confirms an obvious empirical trend. That is, those who have taken advantage of process automation via various technologies have brought increased value to their user base, they have scaled their businesses, and in many ways changed the landscape of the industry they participate. Search and socials implement SEO and other analytical tools to maximize and monetize advertising at a magnitude never seen before. Consumer discretionaries moved from manual ordering and hard goods to software applications and digital deliveries. Financial institutions also recognized banking processes were antiquated. Going to a physical location, handwriting deposit and withdrawal forms, long lines, and paper ledgers were not efficient use of time and money. Therefore, mobile banking was implemented. The success of these re-engineered processes created a better user experience and organically developed an information infrastructure that then could be leveraged for future innovations. This principle lays the groundwork for applications in geosynthetics. A quick historical assessment of geosynthetics does show that it has evolved in many ways thanks to organizations like IGS, IAGI, ASTM, GSI, IFAI, to name a few, and the private industry goers such as engineers, manufacturers, CQA firms, and installers that make up these committees. Developments in governance via the EPA and state DEP for more stringent use of geosynthetics has played a catalyst role. Engineering and materials manufacturing has evolved as well by improving additive formulas to target specific applications and growing catalogs of conformance testing materials to hone in on materials of best fit. Machinery for both manufacturing and installations have also evolved over time. Even post-installation leak detection allow for more dialed-in repairs, whereas in the past, expensive effort was needed for relatively small remedies. With an understanding of successful implementation in other markets and how geosynthetics have evolved to date, we can evaluate potential points of entry for automation technology today. It's important to objectively understand that not every process needs to be automated. The best suitors are those that tend to be the most redundant and manual, because improving those practices will subsequently provide the best return for the industry. We will examine specifically why that is later. The practice of installing geomembranes has been largely stagnant for decades. The last real industry mover, so to speak, was introducing hot wedge seaming versus extrusion fillet seaming. This innovation redefined what was possible as it relates to installation productions and boosted confidence in the endurance of the systems. Both of these improvements played a part in more required use, which ultimately had ripple effects for other stakeholders. More required use meant more designs and installations. More designs and installations meant more manufacturing, so on and so forth. This improvement was so radical because, as we identified before, the technological innovation of the wedge accomplished both user efficiency and it leveraged new associated data to be analyzed for future use. Sticking with the installation phase as an entry point for automation due to its redundant manual nature, it is important to acknowledge that there is recent momentum under this umbrella by some groups that recognize now is the time to evolve our business. Various specification requirements and equipment apparatuses are being reanalyzed and thought about differently. For example, there is a large push to limit the number of destructive samples needed for polymembrane systems. GRI GM20 and 29 give CQA alternative spacing options to lessen frequency, addressing the clear juxtaposition of putting holes in a containment system to assess how well it contains something. While this is only one example of an area industry goers seem to agree needs improvement, it is also a microcosm that illustrates when changing long-lasting industry norms, additional complexities are introduced and must be examined. In the example here, we incorporate material changes, data acquisition welding machines, and post-installation leak checks. Government entities, engineers, and/or owners must assess whether these supplements will not only work as well as its predecessor, but better. Therefore, in order to validate investments in industry evolution, quick, accurate data must accompany any innovation in practice to substantiate efficacy. If not, evolution is slow. The large investments may go to waste because they were developed and then targeted at negligible areas. Right now, that lack of data infrastructure stands in the way of the next dramatic jump in the geosynthetics industry. The QA/QC process of geosynthetic installations is the logical starting point for this proposition, as it performs three key functions when automated and then accepted as an industry norm. First, it improves physical field quality assurance, which provides superior containment system. Second, Automation expedites the review and reporting quality control phase by built-in accuracy analysis, usually performed manually by multiple parties. And third, it creates a centralized database that leverages other future geosynthetic applications.
Standard install workflow requires a robust catalog of information reporting to verify this important environmental construction practice. Currently, the industry handwrites QA/QC documentation. This is hard to comprehend in 2021 considering the magnitude of legitimate field QA needed for this craft and the associated documentation required on a per-acre basis. There are two main identifiable liabilities with this current practice. The first is that it takes a great deal of time throughout the day to keep documentation alone. The real value from having a QA/QC technician and a third-party CQA on site is the quality assurance portion of QA/QC. Assessing constantly changing site conditions, examining proper heat seal and grinding techniques, monitoring welding equipment and deployment methods, and all of the above which are directly related to the system's long-term sustainability. Their role should lean heavily on making sure physical install performance is of good quality, not just that the documentation itself is completed. The second liability is that handwriting allows for far more chance of human error in information fabrication or manipulation. Therefore, automating the record-keeping process to improve speed and reliability for the day-to-day field documentation is a tangible starting point to directly enhance the quality of the whole project. Sticking with the theme of speed, accuracy, and authenticity, we want to rethink the way we catalog these ventures. A big part of the time inefficiency many projects incur is due to redundancy in information gathering. The same information is often drawn on the as-built, then written on the panel placement, and finally transferred over to the SEMA repair reports, all just in slightly different ways. Hand-sketched scale drawings that include all pertinent panel information are extremely labor-intensive to complete, and information can easily be missed. If information is missed during the as-built phase, there will be a ripple effect on future documentation like SEMA repair information that might also go unnoticed. This leaves the door open for future loss and the inability to rely on this information in the future. An existing step in the right direction is the seldom seen GPS as-built specification requirement. Anyone with GPS equipment can shoot points at each panel intersection and grade break, and once that is completed in the field, the points file can eventually become a GPS-coordinated as-built once they're connected by a program like AutoCAD or something similar. However, to populate this GPS as-built, a reference hand drawing is likely already needed to refer back to in order to know what information goes where. Therefore, a simple GPS as-built within these limited parameters does allow for more reliable future use, but it does not only not address speed, it likely makes the process even slower. A more encompassing improvement to the as-built portion of installation QA/QC would be universal use of automated GPS as-built generation. By simply assigning attributes to the GPS points themselves, existing software technology is very capable of automatically generating the line work, panels, repair, destructs, and termination callouts for the as-built. This allows field personnel to quickly see the as-built evolve to address any missing information or shots in real time. Gone will be the days of hand sketching in the field, measuring seams manually with a walking tape, and then cleaning up the as-built in the field trailer, all just to go back out and collect other information. As we'll further examine next, this singular walk of the system will not only produce better quality as-builts and improve user experience, it will also have other downstream effects on the project. By introducing automated GPS as-builts, we now have a much more robust foundation for an improved process as a whole. QA/QC software can then use the abundance of metadata within the original shots to populate the other QC specification requirements. Because the software now knows every panel intersection, every repair and destruct location, every termination, etc., your panel placement log, destruct report, seam control, and repair report all automatically populate appropriately. Maybe even more importantly, the program can now automatically check that the information is within project specifications, which can be entered into the job information setup prior to the start of the project. If the reported information falls out of project specification, users will be notified of the error and can quickly fix their mistake in real time. Undeniably, some information on these submittals will still have to be filled in, requiring the tech to read the information on the liner itself. However, instead of the redundant input of the same names or words hundreds of times in some cases, these parameters are also set up prior to the job. These fill-in areas are replaced with drop-downs accompanied by other preset conditions, such as the standard of waiting for X amount of minutes after an air test. Automation software also makes other important installation checks quicker, such as material inventory checks, seeing if you skipped or missed the number, having the correct number of DTs being pulled per linear feet, and being able to quickly relay production quantities to the superintendent or project team. Finally, with a field software platform, we can also take advantage of cloud technology. So, office personnel or clients may see project progress in real time and can help identify any deficiencies earlier on than by way of manual QA/QC, limiting loss for all stakeholders. As you can see here, by implementing automated GPS as-builts, we can inverse the typical QA/QC workflow by shooting system attributes one time and then using that information to automatically populate other necessary contract submittals. This saves time on the handwork while also providing a better method to not miss any information or log any incorrect information. This approach checks the first box for successful process automation we examined earlier, improved user experience. It provides that freed up time we were looking for to put towards physical field QA. Studies have shown a conservative 25% reduction of field QC documentation time with this automated inverse approach. If we fast forward to field completion of the job, typically there's a large amount of time dedicated to cleaning up the field data and consolidating all the information into a report for submittal. Without field automation, the current state of the practice produces numerous sheets of paper or at best Excel documents that typically need to be compiled, put into a clean format, and printed in a legible manner for professional submission. Thus far, foundational improvements to the field QA/QC means and methods have helped make the physical data collection quicker, more accurate, and more authentic for field personnel. Because all parties within a field setting are now working more effectively, the final phase of an install relating to submittals is now way more easily developed. By having a centralized program, users may simply print submittals upon completion because, as examined previously, the process of checking accuracy is now a streamlined, ongoing effort within the software throughout the project. Therefore, once the final panel, seam, or repair is documented and ran through QA/QC software, the reports can be trusted for accuracy. The process substantially decreases the time allocation needed for report review and submission post-installation. On a per 20-acre basis, this type of systematic field approach results in almost an 80% time reduction requirement by the installation QA/QC engineer who's compiling the final submittal. Furthermore, the liability of missing information on an installer or engineering firm preparing the permit submittal, or ultimately the liability on the owner looking to improve their property, significantly decreases because all information must be complete and correct by the end of the project. The software makes sure of it.
Finally, by making geosynthetic installations more user-friendly and efficient, we have organically developed a database of abundant information we can now leverage for cyclical sustainability within the industry. Pass-fail rates, inventory and waste utilization, repair quantities by type, and GPS locations for all system attributes are all indicators of a geosynthetic venture's success. Depending on who is needing to perform the analytics for any use, these indicators can then be broken down by date, time, temperature, material, personnel, equipment, engineer, job site, and more. As a result, we can apply this data in many ways for future projects and innovations. We can utilize leading-edge tie-in points for accurate next cell or pad designs, subsequent cut-fill anticipations, accurately forecast similar jobs that are coming up for productions and timing. Folks can rely on installer resumes because the information is authentic, both during bidding for ownership groups or organizations like IAGI for certification requirements. Installers can assess employee performance, which materials they struggle with, how well individuals manage material inventory, and so forth. They can then continually improve their practice. With enough R&D and adoption, engineers can rely on the submittal packages for completeness and accuracy to lessen their review time and potentially decrease field day-to-day involvement. We can cross-reference leak surveys to identify locations and participants to improve on future installs with similar attributes. And as we spoke about earlier, we can substantiate success of future innovations by comparing to previous means and methods data, like the GM29 example discussed previously. There are other specifications within geosynthetic systems having to do with subgrade conditions, cover soil placements, and more. We have examined primarily installation deployment and seaming efficiencies in this presentation. However, there are boundless opportunities to integrate ancillary components of a system when a software infrastructure has been established. In conclusion, by implementing automation software into the installation phase of the geosynthetic supply chain, we see immediate improvement to practice in the short term and can leverage a new authentic database for future innovations, both of which have proven to be successful for industry evolution. While there are some geosynthetic QA/QC softwares on the market, none use automated GPS as-built integration, which is the basis to real process improvement. Efficient process automation results in cost savings, limits liability, and improved containment facilities, which ultimately protects our environment and our stakeholders. On behalf of Command Co., thank you for your time, and we look forward to seeing everyone in person soon.